Let's take a minute and talk about the inverse of a matrix. You've all been using this in MATLAB already by just saying perhaps matrix A caret to the -1 power times B. And that comes to the solution by multiplying the solution vector by the inverse value of A, presenting directly the values of X. That's very handy. It works. The question is, why does it work? And if you didn't have MATLAB, how could you program that system in a different piece of software? It does seem silly in a modern world to say, like, oh, we'll choose MATLAB. Or if MATLAB's not available, I'll just use the internet. Or I'll just, Wolfram Alpha will do kind of everything now. If that's not available, I can do Excel, which, yeah, Excel does have a hidden, not well advertised matrix inversion function, but it'll do it. But there are circumstances where you don't have access to a lot of these outside programs, or your company's not willing to pay for some of these things. Or in truth, some of the operations are much more complex and less common than matrix inversion. So you'd like to program some of these methods yourself. Hopefully not plural. I don't know. Whatever. Let's look at the textbook. So inverse of a matrix. Again, the whole point is that if you find the inverse of a matrix, that is going to be equivalent to 1. Or in matrix form, the value of 1 is really the I matrix, the identity matrix. That's the one that has all zeros except for ones down the diagonal from top left to bottom right. So for the matrix inverse, you could say that if you were given some matrix of unknown coefficients of all A's, multiplied it by some big solution matrix of all the different X's, this is actually the unknown values of your inverse matrix, that the answer would be unity, aka the identity matrix. So the starting matrix, I have to be careful which finger I use to point to things, starting matrix times the inverse matrix equals identity. That's the whole thing. A handy way to split this apart, to show you that you can actually solve directly for the inverse, is that if you take the coefficient matrix, multiply it by the first row of the inverse, well, then you get the first, excuse me, that's not a row, that's a column. You know, words. Multiply by the first column of the output. Well, not multiply, it equals the first column of the output. Let's just go through the description again on part 2, since I butchered that one so nicely. All the coefficients in a 4x4 matrix times the second column of the inverse equals the second column of the solution. And you split this apart into 4 different problems, which makes it convenient to solve with any of the preceding matrix solution methods. You could use Gauss separation, you could use Gauss-Jordan, that was the second name I was looking for, solution methods. You could use lower-upper decomposition, which is a particularly useful method because all the coefficient matrices are the same. So the LU decomposition of this large A matrix is exactly the same for all 4 problems. That's one of the most justifiable reasons I've seen for using the LU decomposition method, but you know, whatever. But, so again, if you need a refresher on how to do LU decomposition, well, there's a video on that, but this is, again, you've arrived already at general form of the matrix, so whether you solve it LU, whether you solve it Gauss-Jordan, whether you solve it just Gauss decomposition, up to you. That's pretty standard form. Once you find all the values of X's, you reassemble them back into this original matrix, and you're done for the inverse. Obviously, I'm going over this part quickly. It's not my preferred method. I'm going to show you my preferred method. Gauss-Jordan. So you remember how we did solutions to the general form, where you would just take your coefficient matrix and you would concatenate it with the solution vector. The solution, usually 1 column vector, and then you would do all the row manipulations to end up with identity, where you used to have coefficients, and then the numbers remaining here on the rightmost column would be the answer directly. Well, that's kind of exactly what we're doing again. In fact, the procedure is so similar, all it takes is just a few changes in the code indices, and you can use the exact Gauss-Jordan procedure to find the inverse. The solution you're looking for here is not a particular set of numbers or rows. No. The unknown is actually much bigger. The solution you're looking for is the identity matrix. Okay. So set of coefficients concatenated with the identity matrix. Perform the standard Gauss-Jordan procedure. This is like that meme where it's just like question mark profit. And then you end up with the identity matrix in the left quadrant. Is that a quadrant? There's only 2. The left half. We'll call it halves. Quadrants implies fourths. The left half is the identity matrix now. And the right portion becomes your inverse.